All right, let's go over this together now. So again, like I said, you should now have a separate spot where you write out what I do. Maybe it's the exact same thing you did, maybe not. I'm going to add reasons. And these are reasons you should be able to give on the test next Monday. And that means you need to do more than just listen and take notes. It probably means you need to practice similar kinds of example on your own before Monday. By the way, I will put some sample exams up probably later today. And that does also include, for example, the proof that we did on Monday. You can't expect that you're going to get it unless you practice it, unless you think about it and try to understand. And that can be something that Math Lab can help you with as well. Math Lab is more than just, am I getting the right answers? Math Lab is supposed to help you understand, ideally at least. So let's talk about this. So this is assumed to be a position or distance traveled as a function of time. I didn't give units. That's okay. You know, typical units for distance would be in meters or centimeters or whatever. Maybe kilometers, maybe miles. Typical units for t itself is in seconds. You might wonder, how does that work? I mean, how can meters be equal to seconds to the fourth power? Well, I'm hiding something here. There really would, in a sense, be a constant of proportionality, 1, that would have units of meters per second to the fourth power to make the units work out right. So don't worry about how the units work out exactly here. Find the instantaneous speed at t equals 2. We talked about average speed in class on Monday, and we also talked about instantaneous speed. What is the speed at a given moment in time? Usually speed is distance divided by time. But at a given moment in time, there's no time elapsed. You'd be dividing by 0. That's why we have to think of it in terms of the limit concept. That is the key insight that helps you realize you've got to deal with limits. That equality right there is just the definition of instantaneous speed. Definition of instantaneous speed is the reason for that equality. This equality right there is just the definition of the derivative. Actually, you could just jump from instantaneous speed to this limit without writing the derivative symbol, but we might as well get used to the derivative symbol. So now calculate this limit. And like I showed you on Monday, that means carry the limit sign along for the ride. Don't actually evaluate the limit until the very end, but the limit sign with the h going to 0 needs to be there the whole time until the very end. This function is t to the fourth, so we get 2 plus h to the fourth power minus 2 to the fourth power over h. But now we need to expand that 2 plus h to the fourth power, and the answer is not 2 to the fourth plus h to the fourth. That would be a mistake. That's not what you get when you expand a binomial. We need to use this row of Pascal's triangle. 1, 4, 6, 4, and 1 as the coefficients. 1 first of the coefficient of the first term in there, which is 2, raised to the highest power, 4, times the second thing raised to the 0 power, h to the 0, which is really 1, but I will go ahead and write it anyway. Plus 4 is the next coefficient. It goes times 2 to the third power times h to the first. Take the first thing to the third power and then the second thing to the first power in that next term. The next coefficient is 6, so we get 6 times the first thing squared. These powers of the 2 keep going down by 1 each time, times h squared. The powers of h keep going up by 1 each time. This is the way the binomial theorem works. Then 4 times 2 to the first times h cubed, and then 1 times 2 to the 0 times h to the fourth. That entire thing is an unsimplified version of 2 plus h to the 2 plus h quantity to the fourth. Don't forget to subtract the 2 to the fourth, which is 16, and then divide that whole thing by h. If you do it right for this type of problem, all the terms that do not involve an h will completely cancel. Minus 16 doesn't involve an h, but technically speaking, this one doesn't involve an h either because it's h to the 0, which is 1. Those two things cancel. 16 minus 16. All the other terms in here all involve a factor of h that can now be factored out. And once you've got it factored out, you also simplify. 4 times 2 cubed is 4 times 8 is 32. There's the answer, actually, 32 sitting right there. But you need to show the work to get there. 2 squared is 4 times 6 is 24, but don't forget a factor of h. Right? We don't have a factor of h here because we factored one factor of h out, and that's an h to the first there. When I factor an h out of this one right there, I'm left with an h, because h times h is 8 squared. Factor an h out of the next one, I get plus 8h squared, because h times h squared is h cubed. Factor an h out of this one, use the fact that 2 to the 0 is 1, and I get a plus h cubed. All divided by h. We're almost home free here. Cancel the h's, or better, divide them out is a better way to say that. Here, when I cancel the 16s, it's better to say canceling because I get a 0. 16 minus 16 is 0. Here, when you divide out the h's, you're really left with a 1. H divided by h is 1, as long as I'm not dividing by 0. And what I'm left with is the limit of 32 plus 24h plus 8h squared plus h cubed, that limit as h goes to 0. And now you are justified to plug in h equals 0. Now evaluate this limit. You don't have to show this line that I'm doing on a test, but it doesn't hurt. And for emphasis, I'm doing it. The final answer you could just jump to is 32. And using the units, it would be, it's a speed, so it's in meters per second. You should be able to give reasons for all these other steps here. That equality right there is just using the formula for f. That's all that is. Substitution, you might call that. Substitution. If you want to be a little bit more specific, you could say substitution using the formula for f. F of t is t to the 4th. This next step, I mean, if you want to get fancy, you could call it the binomial theorem, and I guess I will, binomial theorem. But I'd be fine if you just said expansion or algebra or something like that. This next step is simplification and factoring, you might say. Simplification and factoring. I'd be fine if you just said simplification. You could also just say algebra. This step, though, is tricky. It's not just simplification. It's not just algebra. That's part of the reason, but it's not the whole reason. Let me write simplification and some other reason. I hinted at this on Monday. Does anybody remember the other reason I gave for this kind of step where you can divide the h out and say these limits are the same, assuming they exist? Had something to do with holes in graphs. And in what's that? That's actually this step, so you're close. Definition of a limit, which I haven't actually written down because it's kind of complicated. In effect, you can describe it this way. The value of the limit of the function, assuming the limit exists, does not depend on the actual behavior of the function, in this case, at h equals 0. Say that again. The value of this limit here assuming it exists, does not actually, technically, depend on the value of this expression that I'm pointing at when h equals 0. Now, the value of this expression that I'm pointing at when h is 0 is undefined. It doesn't have a value. But that doesn't matter. The limit can still exist. I'd be fine if you said definition of a limit. Sorry that I didn't show that to you there. If you want to be a bit more specific, you could say the value of the limit is independent of what actually happens at, emphasis on the word at, h equals 0. Specifically, when I'm thinking about this as a function of h. You say, how's that a function of h? Well, it's a function of h if you think of h as a variable, which we're really doing since we're letting h go to 0. We're really thinking of it as a variable. Originally, we were thinking of t as the variable. Now, in this expression, since we're plugging in t equals 2 effectively, we're thinking of h as a variable. If you graph this as a function of h, it will be the exact same as this graph, this cubic function of h, except with one point missing at h equals 0. This graph is continuous at h equals 0, but the graph of this one is not. It would have a hole in it, a point missing. But because these functions are the same everywhere but h equals 0, their limits will be the same if the limits exist, and they do exist, and they equal 30, it equals 32. The continuity really comes in this step. Continuity of this function, 32 plus 24h plus 8h squared plus h cubed at h equals 0. That continuity allows me to plug in h equals 0 there, or there, excuse me, to give me 0 there, 0 squared there, 0 cubed right there. And then this very last thing is just simplifying. And I would be okay if you just jumped from here to here. But if you do that, you should say the reason is continuity. The continuity at a point, in this case h equals 0, says that the limit of the function as h goes to 0 is equal to the function value at h equals 0. All along, we don't plug in h equals 0 because we don't want to divide by 0. But then at the end, when we get a continuous function at h equals 0, then we go ahead and plug in h equals 0. That's pretty confusing to many people, but it is what's going on here. Technically speaking, this is exactly what's going on. You should be able to interpret this geometrically. So again, our function is s equals f of t equals t to the 4th. We're talking about the derivative at t equals 2. The function value at t equals 2 is 2 to the 4th is 16. Let's say 16 is right here. Axis not to scale. The graph also goes through 1, 1, which would be way down here. On this scale, the graph of t to the 4th looks about like this. 3 to the 4th is 81. So by the time we get to 3, we'd be up higher than pretty high. Okay, it's not a perfect picture. Looks like a part of a parabola. Technically, it's not. Only quadratics have graphs that are pieces of parabolas or whole parabolas. Though we don't usually worry about that. Again, parabolas have a technical meaning. If you've ever heard of a parabolic mirror or a parabolic telescope, the shape of the mirror, the shape of the telescope has to mirror, pun intended, the shape of a parabola in order to work right. If you make the shape like this, which is technically not a parabola, it won't work right. I'm not going to get into details. We have just found the derivative of this function at 2, f prime of 2, or in Leibniz notation, ds dt evaluated at t equals 2. It's 32 meters per second. That is the slope of the tangent line to this graph at t equals 32. Yes, the tangent line just intersects the curve at one point, but do not think of it that way. It's better to think of it as the graph, the line, the curve looks more and more like as you zoom in closer to the point. That's the better way to think about the tangent line. Its slope is the slope of the curve at that point. And that slope here represents a speed. And the slope of this is f prime of 2, we just found to be 32 meters per second. T is in seconds, and S is in meters. What does that tell you? That tells you that that instant in time, that's how fast you're going. What does that tell you? That tells you, for example, approximately how much further you're going to travel if you go for another, say, 0.1 seconds. If you travel, well, okay, if time goes from t increases from t equals 2 to t equals, say, 2.1, so delta t, which we're calling h in this context, is 0.1. What would be your approximate change in position? Change in distance traveled. The change in distance, change in position would be approximately the rate of change at t equals 2 times the actual change in time. Hey, distance equals rate times time. That's what this means. Approximately, it's an approximation because the speed of 32 meters per second is not a constant speed. The slope doesn't stay constant as time goes up. It keeps getting higher and higher. But if delta t is small, this should be a good approximation. What will it equal? It'll equal 32 times 0.1. 3.2 meters would be your approximate change in position. Distance traveled over that 1/10 of a second. Is that really right? It's not perfect. It's just an approximation. What would the true answer be for the change in position? It would be, the function is t to the fourth. It would be 2.1 to the fourth minus 2 to the fourth. That would be the actual change in position because the function is t to the fourth. Yeah, 3.4481 is the actual change in position in meters. This is an approximation. Somewhat accurate, but not as accurate as you might hope. It gets more accurate the smaller the time interval is. If I use delta t to be 0.01, by the way, the stuff I'm talking about right now is the heart of a lot of calculus. Right now, this is it. If delta t is 0.01 seconds, then delta s, the change in position, would be approximately 32 times 0.01 or 0.32 meters. Is it exactly right? No, but it should be pretty close. And in fact, on a relative scale, closer than this one was. If I take 2.01 to the fourth and subtract 2 to the fourth, I should get an answer pretty close to 0.32. 0.3224. Let's try one more example. If delta t is 0.001, I won't write it down, but if this were 0.001, I get 0.032. 2.001 to the fourth minus 2 to the fourth is the exact change in position. It should be very close to 0.032. Yes. This is the heart of differential calculus right now. This is, if there's anything to remember from this course about derivatives, it's this stuff right now. Say when you maybe eventually have to help your kids with calculus in the future. This is illustrating the idea of the derivative as a linear approximation. The tangent line is approximating the curve. We can see it visually, we can see it numerically. It's an instantaneous rate of change of s with respect to t. And if I multiply the derivative value times small changes in t, it gives me good approximations to the change in distance. And those approximations get better and better the smaller delta t is. That's the heart of what applications of derivatives are all about, right there. Of course, there's plenty of other topics we talk about. For one thing, we apply this idea to many situations, not just physics. For another thing, there are related applications that are challenging. For example, there's optimization. If you've done that before, optimizing functions, there's something called related rates, which are pretty tricky kinds of problems. But it's all related to this key concept and how it relates to the graphs, rates of change, slopes, that kind of thing. Differential calculus. Differential meaning is basically synonymous with derivative. They do have slightly different shades of meaning. Technically speaking, when I say derivative, I'm coming up with something that's derived from the original function. That's why we say it's a derivative. When I use the word differential, historically at least, that's more referring to these quantities in this thing where we pretend this is a fraction, though it's really not. The ds and the dt their official names are differentials. We put them as if they're in a fraction, as if we're dividing, even though that's not really what's going on. But if you pretend it's what is going on, it can give you insights into how calculus is useful. That's why we pretend it that way. That's what Leibniz did, in fact. We call this Leibniz notation. Leibniz was a contemporary of Newton. Basically, Leibniz and Newton discovered calculus at the same time. Newton technically slightly before Leibniz, but Leibniz published sooner than Newton did. Leibniz's notation sticks with us more than Newton's notation does, though, and his terminology. Can I clarify anything? This is really, really key stuff. And again, you can't expect to just listen to me right now and necessarily be able to do this on the exam, especially with reasons. You got to think about it between now and then. Ponder it. Let's try another example. This time, we're going to use, let's continue with physics. This time, we're going to use a function that actually decreases. 1 over t. This is still in meters. T is in seconds still. Though again, how does the units work? You might be thinking, okay, wouldn't the units of this be 1 over seconds then, and that doesn't equal meters? Well, that's fixed by choosing the constant to have appropriate units. The one there, if you made its units be what? Meters times seconds, actually, then the units of seconds would cancel. That's the way you fix the units. Let's find not the instantaneous speed in this case, but the instantaneous velocity. Instantaneous velocity, not speed, at t equals 2 in this example. I did say on Monday that technically speaking, speed is always the absolute value of velocity for one-dimensional motion. If the motion is not one-dimensional, which we will talk about a little bit today, two-dimensional motion, then the speed is said to be the length of the velocity vector. If you're talking about one-dimensional back and forth motion, either left, right, or up and down, then you can think in terms of speed being the absolute value, speed being the absolute value of the velocity. Velocities can be negative. If you're throwing a ball up in the air straight up and then it goes up and then comes back down, it makes sense to make the upward direction positive and the downward direction negative. So as the ball goes upward, the velocity is positive, and as it's coming downward, the velocity is negative. That's a useful thing to be able to keep track of the direction with a sign change from positive to negative. By definition, this is the derivative at 2. The speed is only equal to this. The instantaneous speed is only equal to this when the velocity is positive. So when I wrote instantaneous speed equals f prime of 2, that was a little bit of a fib in general. But for that example, the example we just did, the motion was always in the positive direction, so the speed and velocity were the same. And here it's really better, you could call S a distance, but it's really better to call it a position instead of a distance. Because distance should be positive. Position could be positive, but it could be negative, depending on where you put the origin, 0. Distance always increases. Position could decrease. You could be moving toward the origin. You know, a natural place to put the origin when you're talking about free fall under the Earth's gravity is at the ground level. But, you know, if you dig a hole in the ground and let the ball fall into the hole, then the position could be negative. If the 0 is at ground level. So that is again going to be the limit as h goes to 0 of f of 2 plus h minus f of 2 divided by h. And maybe I should have chosen a different time, like 3 or 4. If this were time 3 here, then this would be time 3, and I'd put a 3 here and here. But I didn't, and I'm not going to change it now. All right, what do? Use the formula for the function. It's 1 over t. You see f of 2 plus h there. That entire expression, 2 plus h, needs to go into that equation in place of t. You need to do 1 over 2 plus h. That is f of 2 plus h. This is the importance of understanding mathematical symbolism, which is part of what we test you on for the placement exam and the skills test. You understand what to do here. Minus f of 2 is just 1/2. All divided by h. That doesn't look so easy, does it? You can solve this. There's a couple different ways to think about it. You could get a common denominator of 2 times, in parentheses, 2 plus h for these fractions in the top, and then subtract them once you've got a common denominator before dividing by h. You also could, this is what I usually do, multiply by a disguised form of 1, where the disguised form of 1, the numerator and the denominator, consist of the product of these 2 denominators here, 2 times 2 plus h, so that you get complete cancellation of those in the top. This is the way that I usually do it, but it's not the only way. I'm multiplying by that so that I get cancellation when I distribute this through the top. That's why I'm doing this. If I do it to the top, I have to compensate by doing it to the bottom. So that I'm not changing this expression. I'm multiplying by a disguised form of 1 here. Just tricks of the trade to know what to do. You're not going to remember it unless you practice it, probably. When you multiply on top, again, you distribute. Multiply it times this first fraction, the 2 plus h's cancel, or divide out is a better way to say it. But the 2 is still there. You're left with the 2. This 2 doesn't cancel with anything. When you multiply times 1/2, the 2's cancel, and you're left with 2 plus h. Very important to put parentheses around the 2 plus h. Do not forget those parentheses. You'll get the wrong answer, probably, yeah. You must have those parentheses there if you want to avoid a mistake. And if you want to get full credit for good work as well, even if you accidentally get the right answer. But don't forget to do it to the bottom. H times this I can write as 2h times 2 plus h. Simplify. 2 minus, distribute this minus sign through. 2 minus 2 is 0. Negative h is, well, just a negative h. Now divide the h's out. Negative h is the same as negative 1 times h. Now you can plug in h equals 0. This is a continuous function at h equals 0. It's not a continuous function at h equals negative 2, but I don't care about h equals negative 2. All I care about is h equals 0. Plug in h equals 0. Negative 1 over 2 times 2 plus 0 is negative 1/4. Reasons? I won't write it this time. Definition of instantaneous velocity. Definition of derivative. Substitution of the function. Put these things into the function. Algebra, or simplification is okay to say. Distributive property was used. I'd be fine just saying either algebra or simplification. More algebra / simplification. Here's the key one key one at least. There's the definition of the limit, meaning, as I said before, it doesn't really matter what happens to this function at h equals 0. This function is undefined at h equals 0, but it equals this one when h is not 0. They're both undefined at h equals negative 2, but I don't really care. So if the limit exists, these limits will be equal because these expressions are equal when h is not 0. And here's another key one. That's the continuity of this function at h equals 0. It fills in the hole for the graph of this one at h equals 0. So that's definition of the derivative. This is continuity. And then finally, just simplification. Negative 1/4, negative 0.25. So what have we found? We found that the instantaneous velocity at t equals 2 is negative. S is decreasing, going down in value. The graph is decreasing. And at 2, the value here is 1/2. Function is 1 over t. 1/2 is 1 over 2. The slope of the tangent is this negative 1/4. Slope equals negative 1/4. So the approximate change in position now, delta S, when delta t is small, is the derivative at t equals 2 times delta t approximately. So that'll be negative 0.25 times delta t. If delta t is, for example, 0.1, Then delta S is approximately negative 0.25 times 0.1, which would be negative 0.025. Does that happen exactly? No, but should be decently close. The value of the position at time 0.5, time 2 is 1/2, 0.5. The position at time 0.1 seconds later is 1 divided by 2.1. What's the change? The change in position is this number, the 0.47619 minus the starting position, negative 0.024, very close to the prediction from the derivative. The change in position being negative means S went down. You're going toward the origin. You're at a positive value of S, but you're going toward the origin. If the elapsed time was even smaller, 0.01, for example, I'd get negative 0.0025. 1 divided by 2.01 minus 1 divided by 2 is the actual change in position. That should be very close to negative 0.0025. Yep, very close to negative 0.0025. This is the heart of differential calculus right here. Can I clarify anything here? I didn't need it because I didn't need to use the binomial theorem. The binomial theorem is for expanding binomials, which means the sum of two things to some power. That's what a binomial means. That's where you use the binomial theorem. There is technically a binomial theorem I could have used here as well, because 2 plus h, I could have thought of it as 2 plus h to the negative 1 power. And there actually is a way to expand that, a negative power binomial, but it involves an infinite series. It's another famous thing that Newton discovered, is how to expand things like that as infinite series. But that's a calculus 2 topic. Does that mean Pascal's triangle goes backwards? Well, not going to get into details. By backwards, I mean upwards instead of downwards. Let's spend our last 15 minutes today thinking about the more precise definition of a limit. This is going to be a challenge here, but it's worth doing. On Friday, besides reviewing for the exam, we will also look at another application that is in one of the lectures, and I hinted at in class here, related to compound interest. We're going to look at the yield rates of bonds related to present values of income streams, you might say. That sounds fancy. It's not as fancy as it sounds, but we can simplify things. Let's talk a little more carefully about what limits really mean. Let's do it through an example. I'm not going to write down the general definition. The limit as x approaches, let's choose the number 3, of x squared, to pick a reasonably simple function, is what I hope you would guess. What do you guess when you look at this? Yeah, 9, 3 squared. Why? Because x squared is a continuous function of x everywhere, no matter what x is, and therefore, by the continuity, since x squared is continuous everywhere, and in particular at x equals 3, I'm being a little sloppy here. I'm not giving the function a name. Maybe I should. F of x equals x squared is continuous everywhere, and in particular at x equals 3. That means you can evaluate the limit at x equals 3. Technically speaking, we haven't proved x squared is continuous everywhere, but that seems reasonable. When you look at its graph, you can draw it without picking up your pencil. It's not a proof, but it should make it seem reasonable. What does this really mean to say this? It means we can make the values of this function, f of x equals x squared, as close as we like to 9 by taking x close enough to 3. Sufficiently close to 3. I'll write that out. This means we can make x squared, f of x equals x squared, as close to 9 as we please, or as we like. I'll say as we please, by taking x itself sufficiently close to 3. That, what I just wrote there, is not a precise definition. What makes it not precise? Because it's kind of vague. What do you mean? What do you mean as close as we please? And what does it mean to be sufficiently close? Those are kind of vague terms. There is a more precise definition describing this, including in the book, involving some Greek letters, an epsilon and a delta. It's on page 59. And what I'm about to talk about here right now is related to that, but I'm not going to get as fancy as the book is. I just want to help you understand this at an intuitive level. Right? Trying to ask and answer some questions here. For example, I will go ahead and use the Greek letters. How close to 3 should x be so that f of x equals x squared is within a distance on a number line of epsilon equals 0.1 units of 9. How close to 3 should x be so that f of x equals x squared, the output of the function, is within a distance of 0.1 units of 9, meaning so f of x equals x squared is between 9 minus epsilon is 9 minus 0.1 is 8.9, and 9 plus epsilon is 9 plus 0.1 is 9.1. Think of x as being a fixed number you'd like to find, and therefore f of x equals x squared is another fixed number. Though we could pick different fixed numbers. How in the world would you answer a question like this? There's a few different ways you can think about it. One of which involves thinking about inequalities and absolute values. And that is talked about in the book. But let me think about it a different way that's probably a little easier. I could try to figure out what values of x give me an output of 8.9 and 9.1? If I set f of x equal to 8.9, what is x? Well, it would be the square root of 8.9, which should be just a little less than 3. Square root of 8.9 is about 2.983. 287. I'll round it to that far. 2.983287. I don't need to go that far, but it's all right. And on the other hand, if I set f of x equal x squared equal to 9.1, that means x is square root of 9.1, which is approximately something a little bit bigger than 3. 9.1, about 3.016621, say. So if x is this number or this number, square root of 8.9 or square root of 9.1, then f of x equals x squared will be 8.9 and 9.1 respectively, exactly 0.1 units away from 9. How far are these numbers away from 3? 3 minus 2.983287, let's see if I can do that in my head, is 0.016713 if I didn't make a mistake. Maybe I better double check it just to make sure. 3 minus 2.983287. 0.016713. How about that? No mistake. And the other one is how far from 3? 3.016621 minus 3 is 0.016621. Hey, those are approximately equally close to 3. Not exactly, but really close. Both about 0.0166 or 67 or so away from 3. So here's the punchline. So if x is, for example, within 0.016 units of 3, look at those two numbers, pick a number smaller than both of them, say ever so slightly, or maybe even smaller. Then f of x equals x squared will be within 0.1 units. Epsilon equals 0.1 units of 9. To be within 0.016 units of 3 means x is between 2.984 and 3.016. Because 3 minus 0.016 is 2.984. Now you can use your calculator to help you believe this. How? Go to your y equals screen, clear out anything that needs to be cleared out. Plug in the function x squared. Then pick an appropriate window. Here's the hard part, picking an appropriate window. Let x min and x max be these two numbers, 2.984 and 3.016. Oh, did I forget to plug the function in? Oh, yeah, okay, the function's in there. Okay, x squared. 2.984 and 3.016. And you know, the x scale here makes the tick marks so far apart. We could make this be, say, 0, 0, 1. And then pick the y min and y max to be 8.9 to 9.1. And make the tick marks there, maybe 0.01 units apart. So this window here in the y direction, these numbers are 0.1 units away from 9, epsilon units away from 9. The x direction, these two numbers are 0.016 units away from 3. They are closer than these two numbers are to 3. So what does all this mean? It means if I graph this now, I should see the entire graph in this window. It should exit the window through the left and right sides, not the top or the bottom, just barely. If I did not pick x to be close enough to 3, if I pick this to be, say, 2.98 instead of 2.984, and this to be 3.02 instead of 3.016, watch now, the graph will exit through the top and the bottom now. I'm not close enough to 3 on this window here to make the outputs within 0.1 units of 9. I need to make x closer to 3. Let me go back to what I originally had, 2.984 and 3.016. Now it exits the left and right sides. For all x between 2.984 and 3.016, the y coordinates are between 2.9 and 3.1. Now you might be saying, what in the world is going on here? What is this all about? And if you are, that's probably good. You should wonder what it's about. Here's what it's about. The fact that this limit is 9 means I can play this game and always succeed, no matter how small this number is. I pick 0.1 units away. I could pick 0.01 units away, or 0.001 units away, or 0.0000001 units away, or 10 to the negative million power units away. I will be able to succeed in figuring out how close x needs to be to 3 to make f of x within that far of 9. The fact that the limit truly is 9 means I will always succeed. If you kind of get that, that's good. If you still don't get it, it's understandable. This is a hard concept. The fact that the limit is not, for example, 8.9 means that if I try to get within 0.1 units of 8.9, for example, I will not succeed. The fact that 9 is not equal to 8.99, the limit is not 8.99, means that if I use an 8.99 there and an epsilon is 0.01, I will not succeed. That's also good to think about why the limit is 9 and not something else even very close to 9. Do the reading to try to supplement your understanding. We'll talk more about it on Friday, as well as that application and review for the exam next Monday. Have a good day.